Good afternoon, class. We are looking at Module 5, covering chapters 10, 11, and 12. Here's chapter 12, Analysis of Variance, also known as ANOVA. I'm going to ask you to help me reading, please. Here's chapter 12, Analysis of Variance. Could somebody read this, please?
One-way analysis of variance, ANOVA, is used for tests of hypotheses that three or more populations have means that are all equal, as in H null, mu1 equals mu2 equals mu3, by analyzing sample variances. One-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into the different categories. The populations have the same variance.
Sigma squared.
Sigma squared, or standard deviation sigma.
Perfect. Please continue.
In the F test for analysis of variance, or ANOVA, two different estimates of the population variance are made. The first estimate is called the between group variance, and it involves finding the variance of the means. The second estimate, the within group variance, is made by computing the variance using all the data and is not affected by differences in the means.
Perfect. Please continue.
If there is no difference in the means, the between group variance will be approximately equal to the within group variance, and the F test value will be close to 1. Do not reject null hypothesis. If the means differ significantly, the between group variance will be much larger than the within group variance. The F test will be significantly greater than 1. Reject null hypothesis.
Looking like that because the F test is S1 squared over S2 squared.
The ANOVA test is right-tailed because only large values of the test statistic cause us to reject equality of the population means.
And finally,
other statistical tests, Sheffield test and the Tukey test, are used to find where the difference exists. Although t-test is commonly used to compare two means, it should not be used to compare three or more.
Perfect. The idea is that when we have two samples, two populations, we use the t-test. What happens when we have more than two? We use analysis of variance. Could somebody read the question, please?
Weights in kg of cypress trees were obtained from trees planted in the sandy and dry area. They were given different treatments as indicated. Fill up the table below and use a 0.05 significance level to test the claim that the four treatment categories factors yield cypress trees with the same mean weight.
Perfect. Thanks. Notice we have this group, no treatment. We have this group, we are giving them fertilizers. In this group, irrigation. In this group, both fertilizer and irrigation, and that's why we have four different groups. In essence, four different categories, four treatments. So between them, we want to see what's the difference, and within them. So let's do some preliminary calculation. And again, it's done by a calculator. First, n is the count. We have 1, 2, 3, 4, 5. All of them happen to have n equals 5. Then the sum, we're going to add them up. Then the average, we divide the sum by 5. And then s squared, the summation of x. I'm going to remind you of the formula. Let me write it down. D s squared is summation of x minus x bar quantity squared over n minus 1. So, of course, not done by hand, and we have those values. All right. Let's do some calculation. We want to see how this one gets filled up. We want to find X bar, or the grand mean. Meaning, what is the mean of everything? So add all of these numbers all the way from here to here and divide by 4 times 520. So the very first number is 0.24. The next one is 1.69. Go all the way to the second column, third column, fourth column. Then last one is 0.95, and however many, because each one is 4 times 520. That's the answer. We call it X bar of GM, grand mean. Let me write that. Okay. Just clean this mess because I need this space, everybody. SS sub V. We want the sum squared in between, which is n sub I times xi bar minus x bar gm squared. That's the between sum of squares, but in between the 4 groups. So what is n sub I? For example, for this group is 5. It so happened to be the same for all of them. What is this? Look at this group. What is the average? 1.19. So 1.19 minus this grand mean. So this minus this, square it times 5. Then this one, 0.884 minus this, square it times 5. Again, it so happened that they're all 5, but they may not be times the numbers, okay? For the next one, 1.194 minus this one, square it times 5. For the last one, 1.106 minus this one, square it times 5. See? And that's the sum of squares between treatments. You do the math. So we put this number here. That's how you fill it up. Now, K minus 1, we have a 1, 2, 3, 4 categories. 4 minus 1. Remember, degrees of freedom is n minus 1. So 4 minus 1. We have K minus 1 here is 3. And n minus K, 20 minus 4, or 16 goes in here. And the sum is 19. Just to, again, think about the concept. Degrees of freedom is n minus 1. So the whole thing, we have 4 times 5, 20 minus 1 is 19. So that works out. We have 1, 2, 3, 4 categories, so 3 of them. For each group, degrees of freedom is what? 4 minus 1, 5 minus 1, n minus 1, 5 minus 1. For this one is 4, 4, 4, 4. There are 4 of them. 4 times 4 is 16. So they will add up. 3 and 16 equals 90. The next one is to calculate MSB, the mean square. The mean square we divide by K minus 1, which is 3, or 1, 2, 3, 4 minus 1. So this value we divide by 3. And we put it here. The next one is to find the sum of squares within. The formula is the summation of n sub I minus 1 s sub I squared. So n sub I minus 1. So you go to this group, all of them, n sub I minus 1 is 5, minus 1 is 4, this is 4, this is 4, this is 4. So for this one is 4 times this number s squared. For this one is 4 times this number. For this group is 4 times this number. For this group is 4 times this number. If n was different, whatever that number was, minus 1. And add them up. And this is the sum of squares within. So we put it there. And the sum of square total, you just add them up. Sum of square total. Now, to get sum of square total, it's easier when we have these two to add them up. If the two are not given and you're only interested in sum of square total, you can do that, the concept of x minus x bar quantity squared. So you say this number minus this number quantity squared plus this number minus this number quantity squared all the way to the last one. That should give you the same answer. And so again, for this, we have to divide by 16 to find the mean square within. This is the mean square. Or between, this is the mean square within. And the F test is the ratio between the two. This and this one. The ratio of these two is the F. Point 3897. In essence, that's the test statistic. So I hope you see how the calculation works here. It's very straightforward. If you look at this column, they should add up. Here's the total. If this is the column, one of them is missing, you should be able to do that. As long as we have these two columns, we can get these two. And as long as we have these two, the ratio is this. So you should know how to calculate this. Now, when we go to the next page, I'm going to use the same table we calculated. And since we are using the technology, it also gives us more information in that we have the p-value and the critical value and so forth. But in any event, let's do the test of hypothesis. H0, mu1 equals mu2 equals mu3 equals mu sub 4. We go as many as we have. We have 4 categories. If we have more, we go more. If we have less, and that happened to be the claim in this question. At least one of the treatments has a population mean that is different from the other, and it makes a drawing tail test. One of those are not equal. By the way, the reason this is the claim, because we are supposed to fill it up and then check to see they yield with the same mean weight. So because of this statement, it becomes the claim. All right, test statistic. That's it, it's been calculated. F is 0.38974. Critical value. Well, critical value, I have it here again, the Excel in this case, or any other technology has given us the answer. However, if you were to find that with the F distribution, you need two things. You need degrees of freedom of the numerator, okay? And that would be 4 categories minus 1, which makes it 3. And the denominator is 20 minus 4, or 16. And alpha of 0.05 from the F distribution table. We have this number. You can go with the table. Just use the technology, right? Now, if you look at the graph, this is area 0.05. This is the critical value of 3.2389, and this is your F value for the test statistic, which is way into the non-rejection region. So fail to reject H0. And by the way, if I want the p-value, would be this, which is way larger than alpha, as far as, getting it. So this is the p-value, which is larger than alpha 0.05. So whether I compare two numbers, the traditional method, or two areas, the p-value method fail to reject H0. So if you're not rejecting H0, therefore you're not rejecting the claim becomes true. Fail to reject H0, the claim is true. There is sufficient evidence to support the claim that four population means are all the same. We conclude that the four treatments do result in cypress trees with the same weight. It's extremely important that in the beginning you figure out where the claim goes so you can answer the question accordingly. Here's the last question. Could somebody read that?
Given the readability scores summarized in the following table and the significance level of alpha equals 0.05, use technology to test the claim that the three samples come from populations with means that are not all the same.
Excellent. You have to run technology. So first and foremost, in X bar and S, that's easy. When you count N is 12, then X bar, add them up, divide by 12, and then S, summation of X minus X bar quantity squared over N minus 1, and technology will answer that. If you run an Excel, it gives you this table that we have seen. So let's do the test of hypothesis. H0 mu1 equals mu2 equals mu3 because we have only 3 sets. Okay. At least one mean is different. That makes it right tail and the claim with means that are not all the same. Look at this one. Because of this, we make this the claim. Well, here's the test statistic. 9.46949. Here's the critical value. Degrees of freedom for the numerator is 3 minus 1 or 2. For the denominator is 3 times 12 minus 3 or 33. And the table, F is 3.2849 or Excel. So when you compare, you can see that the test statistic is way into the rejection region because it's way larger than the critical value. So as far as the p-value, by the way, would be the area to the right of that. This would be the p-value. So, and the p-value happened to be there too. And so that's way less than alpha of 0.05. Both cases, whether I compare the two numbers, that means critical value versus the test statistic, or the two areas, alpha versus the p-value, reject H0 because it's way into the rejection. So if you're rejecting H0, that means you're not rejecting H1, you're not rejecting the claim becomes true and you're right. Reject H0, the claim is true. There is sufficient evidence to support the claim that the three population means are not all the same. We conclude that those books have readability levels that are not all the same. So you just reword this for the third part, everybody. You reword this. I want to show you also TI. You look for one-way ANOVA. First, you clear list the list that you need, and we need 1, 2, 3 lists, and we put those. So first in L1, you put those 58.2, 73.4, and so forth. For the second list, you put rolling 85.3, 84.3, and so forth. And the last one, Tolstoy, you put 69.4, 64.2. So you have the 3 lists. ANOVA, and you put L1, L2, L3, and it will do the job. And take a look, see what it gives us. And you run it through. This is the test statistic we had here. This is the p-value we had here. So take a look at the p-value and the test statistic here. Degrees of freedom is 2. The sum of squares in between and the mean squares for in between. Over here, the sum of squares within the mean of that, and of course, degrees of freedom. So everything is there.